Today's class, we are going to continue with our derivation for permanent magnet synchronous motor. So last class, we looked at how to derive the inductance of the permanent magnet motor. So before we jump into and kind of revisit that topic, let me just quickly correct a mistake from last class. Towards the end, when Jonah asked what NSP is, in a hurry, I wrote 2 by P times NS. There should be no 2 there. There is just NS by P. Okay, so that's my mistake. So if you had 100 conductors in your motor, and let's say the number of poles is 2, the number of turns, stator turns, is going to be NC divided by 2, which is going to be 50. And then the number of turns per pole is NS divided by the number of poles. So it's going to be 25, right? So the 2 factor should not be there from the end of last week's lecture. And the second thing, in the homework, I asked you for the speed of the motor for different frequencies. So we've already seen that omega mech, the rotational speed of the rotor, is 2 pi p times the electrical frequency, omega e, where omega e itself is 2 times pi times the electrical frequency that you apply on the stator voltages, right? So as we will see today, there are 2 operating speeds at which the permanent magnet synchronous motor can rotate. If it is rotating, it will rotate only at this speed, right? But there is also another possibility that you have applied too much load torque and the rotor has come to stop. When we do a demo, we look at that condition. In which case, that is also a steady state operating point, which is basically if the load is too large, the speed would go to 0. All right, so that's another condition. So there are 2 answers for the question. Make sure you answer both of those. So this itself, commonly in the textbook, you will see the formula as 120 F by P, right? That comes from the fact that if you substitute those values, so 2 by P times 2 pi F, that would be radians per second. And we typically like to express it as rotations. So every rotation will have 2 pi radians. So 2 pi F divided by 2 pi, that will give you rotations per second. So this cancels. And when we talk about the motors, we usually represent it as rotations per minute. So every minute has 60 seconds, so there will be 2 divided by pi times F times 60, which gives you 120 F by P. Alright, this will be your speed in RPM, rotations per minute. Okay, so this is the formula you typically see in many textbooks and many manuals. Sometimes they use the formula 60 F by P. That comes from the fact that instead of using the number of poles, in our case it's 2 poles, they use what's called pole pair. So every north and south, they club it as 1 pole pair, right? So I don't want to introduce this term in the lecture because it's quite confusing. Some people use small p for pole, large P for pole pair, and some people do the opposite. So it's quite confusing. But just understand the concept throughout the lecture going forward and whatever we have done so far. I've already talked about poles. So the pole number is always even. If there's a north, there will be an associated south. So the pole numbers will be 2, 4, 6, and so on and so forth. Pole pairs can be odd. 6 pole would have 3 pole pairs. So that is why the formula can be different from what you might see in the textbooks and what you are doing in the class, right? But we'll stick with this pole. We'll never talk about pole pairs. Okay. So last class, anybody has any questions so far? Okay. So last class, we looked at the deriving the inductance. We did it in 2 methods. First one is using the energy density method, where we know the energy in the air gap, right? There's a B field in the air gap, and we know that with any associated B field, there is an associated energy that came from the electrical system that energized, created the current, and then created the magnetic field there. So if this B field in the air gap was just a constant throughout the air gap, then to find the energy, it's quite straightforward. You just figure out what the B field is, and then multiply by the volume of this hollow cylinder that you have, right? That would have given you from the energy density. From our energy density formula, you have half mu naught B square. If B is constant, you know the energy density at every single point. To get the total energy, just multiply the energy density by the hollow volume of the air gap. There is no H field in the ion. There is no H field in the rotor. In our ideal case, where we assume the ion is not saturated, or even better, ion has infinite permeability. In that case, there is no H field either here or here. There is no MMF dropped either here or here. All the MMF is just dropped here. So all the energy is just stored within this region where the MMF gets dropped. All right. So since our B field is varying in the air gap, which we have already seen what the formula is, right? Mu naught NSP divided by G times IA cos of theta just for one field. So right now we are only considering a single coil, just the A phase coil alone. We are not worried about what the B and the C phase coils are up to. So for that we have the B field there, and the energy density is just mu naught B square divided by 2 mu naught, which you have derived in the past. So you substitute the B value, you have the energy density at every single tiny point in the air gap. Now to get the total energy, since the B field is varying and it's not a constant, you have to set it up as an integral problem at this point. So we are going to consider a tiny portion in the air gap and look at the volume of the tiny portion of the air gap. And if the incremental volume tends towards zero, then the B field across that volume can be assumed to be a constant. So with that in mind, the energy across that incremental volume that we have there is just going to be the U times the tiny incremental volume. So U, we get it from substituting this B value here and substituting this U value here. We have this expression. And then the dV is just this total length. You can consider it to be a cylindrical structure, not a cylindrical cuboidal structure. So it has a length L, this length is Lg. And then this total length, the rotor radius is R, and we are spreading across some angle alpha, d alpha, incremental angle. So that we R d alpha. Okay, so substitute all of those values. So substitute all of those values, and we did the integral over the full volume, because every portion there is some energy stored, and you integrate the full volume going from 0 to 2 pi, and we ended up with the formula. Energy is mu naught pi RL divided by energy NSP square times 2 by P times IA square. You can cancel this IA squares, right? Because this whole thing must be equal to half Li square from our expression for energy stored in an inductor. And then we got our inductance to be equal to, there is 1 by 2. Right, so we got an inductance to be mu naught pi RL divided by energy NSP square times 2 by P. So this is the inductance of a single phase for one pole pair of the phase. So here I have just drawn the magnetic field for a single pole pair, a north and a south, right? But in case of p-pole motor, let's say 4-pole motor, you would have fields here going out, fields here coming in, fields here going out, and then fields here coming in. Right, so you'll have multiple B fields. The derivation that I've done here is just for one set of pole pair. So if I had 4 poles, it will just be this half of the motor alone, what the inductance would be due to that set of coils. If I had 6 poles, it will be just this one 60 degree plus the other 60 degree, just across this 120 degrees what the inductance is. And once we have that inductance, we have multiple ways of connecting those pole pairs, the windings creating those pole pairs. We can put them in parallel, we can put them in series. If we put them in series, this would just be P by 2 times this total inductance across the phase, and this 2 by P and the P by 2 would cancel out. If you put them in parallel, you will divide it by a factor of P by 2. Alright, so it will become 2 by P the whole square effectively. The inductance would come down. When would you put them in parallel? When would you put them in series? When do you want to connect these windings in parallel? More current. When would you want to connect them in series? More voltage. When your operating voltage is very large, you will put them in parallel series. When your operating current is quite large, you will put them in parallel. Right? Anybody has any questions so far about the derivation for the inductance? So you use the same process all over again when we go to induction motor to derive the inductance in the air gap. And this is a quite powerful tool. You can use it again for different motors. So right now we are only considering sinusoidally distributed winding. In most motors, especially for lower powers, generators will typically be sinusoidally wound. But for EV motors and those that you use with a large pole count, the distinction between sinusoidal and concentrated windings starts to disappear. And there you would have to rederive these equations because the windings are no longer sinusoidally distributed. This only holds true for the distribution that we have. If the winding distribution changes in a different motor that you work in the future, you go through the same process to rederive the inductance for that particular winding set, right? Okay, so the second way of doing the same inductance derivation, this is not just to exercise our math knowledge. There is a purpose for doing this that you will see today. So the second method is we are going to look at what the flux linking all the A-phase coils is. And if we know what the flux linking it is, we know from our formula up here that lambda, which is the flux linkage that we introduced last class, is equal to the inductance times the current. Basically using our previous expression, LdI by dt, we brought the L out when L wasn't changing, but that's no longer the case. When we go to induction motor, L will change, so we're bringing that back in. And then N d phi by dt from our Faraday's law. Again, N is not changing, we can bring that in. So we have d n phi by dt. So N5, which is flux linkage, is equal to Li. So the idea is you have to get a, at this point, I hope all of you have an intuitive feel for fluxes. Flux linkage is just, so if you have some coil and it's creating some flux phi, this flux goes and links another coil. Let's say there is n number of turns, N2, N1, right? The flux linkage would be of the second coil is N2 times phi. That's it. Because each of those coils, when flux changes across it, is going to create an EMF. And if there are n coils, those EMF adds up. Right? That is what we are capturing by multiplying that N2 times phi. So that when we do the d lambda by dt, that will give us our EMF, and that lambda captures all the fact that n number of coils are linking to the single flux phi. Right? So that's what we are doing by this multiplication there. So we wanted to figure out, so again the problem is that if the number of conductors is equally distributed like a DC motor, this is a very simple problem to solve. You just figure out the flux through any single coil and then multiply by the number of coils you have, and you'll have your solution right there for the flux linkage. But in our case, there is a bit of a problem. First, the B field is varying within the air gap, and the conductor distribution is also varying. So we just cannot directly take the flux going through any one particular loop and multiply by the total number of conductors and hope that will be the flux linkage. That is not the case, because coils here would link differently compared to the coils in the vertical direction, because there are more number of conductors here. Flux might be whatever it is, or it's linking much more number of conductors. But if you look at this direction, there are no conductors here. There is no flux linking those set of coils along the x-axis. So that number starts to turn. So again, we'll have to set it up as an integral problem. So there are two challenges now. So setting up the integral problem that's being done on the right. The other problem is, if I take this loop, right, what does this formula say? N d phi by dt, that's basically the flux crossing through the loop that we are interested in. If you do the differential of it, that will be equal to the EMF that we EMF from our Faraday's law. So we need to figure out, say, this is the loop that we are interested in, and figuring what the voltage across it is. You have to figure out what the EMF flux through this coil is. Right? So this is a 3D structure. It goes all the way. Right? So it's a vertical motor. We're just taking one slice of it, and we are analyzing the B field, but it's a motor that goes all the way down. The conductors coming out of the page, going in, coming back, closing, and doing this 3 times. So it's basically the flux through going through the whole loop. So it's quite a complicated picture of figuring out what the flux, what the B field in the rotor is going to be, because it's going to have different structures based on whether you have slots on the rotor, whether you have a rotor shaft, and the different things would contribute to how the B field looks like. So we cannot know by analytical expression what the B field in the rotor would look like. But one thing we do know, the answer that Jonah gave, is the B field in the air gap is well known. So once we know the B field in the air gap, if we want to figure out what the flux through this surface is, all I got to do is so I want to figure out what the flux coming out of the surface is. That is going to be same as the flux entering this surface. Right? Here is the air gap. This is the rotor, just half of the rotor. So this slice of the rotor alone we are visualizing. I cannot figure out what the B field across this section is, because it's quite a complicated picture. But I know exactly what the B field at every single point in the air gap is. So to figure out the flux, all I need to do is figure out the flux entering this semicircle. That will be the same as the flux leaving this rectangular surface that I have on this side. Right, and this comes from our Gauss's law for magnetics. If you go around a closed volume and integrate the magnetic field, you would end up getting the net to be 0, because there are no magnetic monopoles. Whatever field lines leave must be the same field lines that come in. So putting that into this expression here, let's call this the surface 1 and that one the surface 2. So this is surface 1. This whole thing is surface 2, like a paper bent over. And then if you do the summation of these two, that should be equal to 0. So the flux leaving the loop is just going to be the negative of the flux entering from this side on the surface. And that is a pretty simple problem to solve, because we know the flux at every point in the air gap, right? So starting with some angle alpha, so B of alpha, plugging into our B expression there, we have this equation right there. And to figure out the flux, we just have to multiply it by, oops. So we have to multiply that by, again, a tiny cross section. So if you take some radius r and at some angle alpha, so this would be R times d alpha, and the cross-sectional area of that would be R d alpha times total length of the axial length of your rotor. So here R times L times d alpha. Right? So once you do that integral, basically integral of cos alpha is just going to be negative sine alpha, and the negative negative cancel. So you have sine alpha, sine of alpha plus pi plus minus sine of alpha. That will just give you 2 sine alpha. That's what we have here. Right? So this is basically the flux linking this particular set of conductors that I've chosen. Right? That's all we have figured out. We have just figured out the phi going through this particular loop. But then this motor has a bunch of windings at other places as well. So we have some conductors here, we have some more conductors here, right? And then more and more conductors across all across the motor. So in this case, we're only deriving to keep it simple for a two-pole case, and then we'll finally generalize it to a p-pole case as we did before. Right? So we have done it for a single loop. The idea is to figure out what the flux linking all the other loops are. So this is the flux linkage for the single loop that we have there. So we already got our phi expression of times Z. So this is our expression for the flux through that particular loop. And then we know the number of conductors at that location. So how do I get the number of conductors at this location? So this angle is again some choose alpha. So this spread is some d alpha. I take the conductor density, multiply by d alpha, and I'll get the total number of conductors here. Right? If I do the integration from some angle to the other angle, I'll get the total number of conductors in the slot. If the d alpha is small enough, instead of doing the integration, I can just multiply the term. Right? Because assuming that this function does not vary over the incremental surface that I've chosen, incremental length I've chosen, then I can just make it a multiplication instead of an integration for the incremental distance. So this is the total flux linking the number of coils that are there. To get the full flux through the A-phase winding, I basically do the integration of that tiny flux linkage that I've calculated. Right? What will be the limits of this integration? When I did the computation through the energy method, the limits of the integration was basically the full area, right? Going from 0 to 2 pi. What will be the limits of integration for this? It's going to be 0 to 2 pi. Assume it's a two-pole motor. 0 to pi. 0 to pi. Because every time I consider the loop on the top, conductor on the top, the loop is formed by a combination of conductors on the top and conductors on the bottom. Right? So all I have to do is sweep from 0 to pi. I will consider the full loop. Basically, this conductor with this conductor forms a loop. This conductor forms a loop. This with this forms a loop. All I have to do is just half the motor. The loop is complete for the other half. If you do 0 to 2 pi again, like you did for the energy, then you will be double counting it and you'll have double the value. Right? So do the integration from 0 to pi. Again, everywhere there is a RL term missing. Right? So once you do that integration, you would end up with our expression that basically comes out to integration of sine square theta from 0 to pi, and then we give pi by 2, and you end up with the same expression as we had before. So your inductance is mu naught pi RL divided by Lg times NSP square. We are missing the 2 by p factor because in this case we derive for a two-pole motor, so we end up with just this expression. But if you go through the process again, but with a p-pole machine, so introduce everywhere here a factor of p by 2. P by 2. This term would change because of the p by 2 integral. There should be some coefficient that comes there, like 2 by p, I think. And then again here p by 2. And then the rest of it would fall into place. If I go to a p-pole machine, is this sufficient? Just multiply by p by 2, or would this also change? For the conductor density distribution, the conductor density distribution for a p-pole machine would have sine of p by 2 times alpha. Would the magnitude also change for the conductor density distribution function? No? Okay, so the answer is again. It will always be ns by 2. This is the derivation we did at the beginning of last class, where we showed irrespective of the number of poles, the magnitude of it always comes out to be ns by 2. Right? Even for a p-pole machine. If you remember, we had some n peak times 4 by p is equal to 2 by p times ns, and that's how we ended up with n peak is equal to ns by 2 irrespective of the number of poles. But the angle part fork itself will start to change. Okay? So these are the derivations so far. Does anyone have any questions? Any other question? Right. So today's class, we are going to extend this derivation a little bit further. What we have done is, whatever in the flux linkage that I have there, that is the flux linking A phase coil due to current in the A phase coil. So I'm going to rewrite this in this notation, right? So every time I write this, this means that it's the flux linking the A phase coil due to current in the A phase coil. Now we are going to start to introduce the other phase coils as well, the B phase windings and the C phase winding. So before we do that, let's go back to the question I had asked in the midterm exam. So where I had given you one coil and I had given you the current through the coil, and it's going to establish some flux phi, which is quite easy to calculate, right? You can just look at the current and then whatever the flux comes out based on the reluctance of the core. I think I had some air gap too, just to complicate the problem. Once I have this flux through this coil, you can figure out what the EMF is going to be, right? I think I varied this current sinusoidally as well. Otherwise, they wouldn't be EMF in the coil. So basically, the differential of this flux d phi by dt times the number of turns in this coil. Let's say it's N1, N2. That is going to give me the EMF E1. So E1 is just going to be equal to N1 times d phi by dt. And let's say the second coil was open circuited. I didn't provide any current in the second coil. What is going to be the EMF across the second coil? What is going to be the flux link? Okay, let's start with this. What is the flux linkage lambda for the first coil? Yep.
The N1 times phi.
Okay. So lambda linking the first coil, lambda 1, is going to be N1 times phi. Similarly, lambda linking the second coil is going to be N2 times phi. Notice that the flux is created by the first coil though. Yep, really.
Is E1, is that by dz? Is it d phi by dz?
Oh, dt, sorry. Faraday's law.
Oh, okay, sounds good. It's just confused. Thank you.
Anyways, so lambda in the second coil is N2 times phi, right? The same flux links into the second coil, but the current that created the flux was due to the first coil though. All right, so even though if the coil needn't have had current through it, it can still experience an EMF across it. So if I look at what the voltage E2 is going to be, that is going to be d lambda 2 divided by dt. Right, so let's make this even clear. This is flux due to current in the coil 1. So flux in the coil 1 creating EMF across coil 2. So you're going to see similar thing in our motor as well, where when we have current flowing through the B phase, that is going to create its own B field in the air gap. But that B field is going to link with the coils of the A phase conductor. Same as this case, where let's, instead of calling this N1, N2, let's call this B phase. Let's call this B phase. Let's call this flux in the B phase. Let's call this second, the other winding A phase. And let's call this A phase. Right? So even though there is a flux in the B phase winding due to current in B phase winding, that flux is going to link with the A phase coil as well because they're all wound on the same iron core. And that flux linkage is in turn going to create an EMF across the A phase coil. Right? So this is our mutual coupling. So what we calculated here, the previous computation that we have. So this inductance is our self-inductance. Right? So this is the inductance. If you pass a current in the A phase, it will create a flux in the air gap which will link to its own windings. And the flux linkage lambda would be L self times the current in the A phase. So flux in the A phase due to current in the A phase, flux linkage in the A phase due to current in the A phase is just going to be the self-inductance times the current in the A phase. Okay. Now we are going to look at the other one where we have current in the B phase, but it somehow links to the A phase winding. Right? So in this case, we can do the same thing the other way around as well. When you have current passing through the first coil, it is going to create its own flux, which then links to the second coil as well. Right? So the way you write this out is flux linking the A phase coil, or let me go back to the notation, first coil would be equal to its own self-inductance times the current within its own coil plus some mutual inductance, basically the mutual coupling between this and this, times the current in the second coil. And then the same for the flux in the second coil, that is going to be its own self-inductance times the current in its own coil plus a mutual inductance times the current in the first coil. You can just put this in a nice matrix notation, L self, Lm, Lm. Let me make it even clear, L mutual, and L self times I1, I2 is equal to lambda 1, lambda 2. Right? So due to its own current, there is some flux linking it. Due to other phase current, there's going to be a flux linking it. So let's do the same thing for our permanent magnet motor. So instead of redoing the whole derivation again, let me just take the components of it, or that is of critical importance to us. So let's start off from the d lambda value n times d phi. Okay. So what I'm going to be interested in calculating is flux linking A phase coil due to current in the C phase coil. What will my dn term be? Is this dn the distribution of the A phase coil or the B phase coil? So go back to this notation. I'm interested in the flux linking the A phase coil due to currents in the B phase coil, right? So which terms am I interested in?
B phase.
B phase, right? Anyone else? Or everybody B phase? Right? So coming back to this expression, the flux is due to the B phase coil, but I'm interested in the flux linking the A phase coil. So the answer I think we gave was the answer Na times phi or Nb times phi. If I'm interested in the flux linking the A phase coil due to flux from the B phase, which end did I use? Thank you. Right, so this was previously our lambda 2. So lambda A was Na times phi B. Right, we are interested in the flux linking the A phase coil due to currents in the B phase coil. So I have currents going in the B phase coil that is setting up its own flux phi B, and that is then linking into a A phase coil with the number of turns being Na, and that is creating the flux linkage lambda A, which is equal to Na times phi B. Okay, so again here, it is the distribution density of the A phase, but the flux coming from the B phase currents. Right, so the currents in the B phase creating some flux linking with the A phase turns. So the interested turns I am in A phase, because I'm still computing the total flux linking the A phase. I haven't considered what happens to the B phase yet. Right, but I'm interested what the effect of the B phase is on the A phase. Everybody clear so far? What I choose? Okay. So in that expression, everything remains same for the first part. So it is n divided by 2 sine of alpha. Right, that part doesn't change on the top equation. I'm going to leave out the p by 2, just looking at the 2-pole case for continuity. And then the second portion, 2 times mu naught NSP divided by LG, 2 times mu naught RL NSP divided by LG times sine of time phi d. What would this be? Would that be sine of alpha? Take an educated guess.
Alpha minus 2 pi over 3.
Alpha minus 2 pi over 3. Because what is this term? This is term coming from the flux in the B phase due to its own currents. And we know from our simulations that we have seen so far, all the animations, that if the flux in the A phase is along this direction, flux in the B phase is going to be 120-degree phase shifted. And its distribution is going to be its own angle minus 2 pi by 3. That's how the flux in the B phase is distributed. So the flux term is from the B phase, the conductor density is from the A phase. If you do this integration, pretty straightforward integration to do, same thing, whatever we did there, do the same one, plug it into Mathematica, and it's going to spit out the solution for you. The result would come out to negative 1 by 2. The negative term is quite important. Mu naught pi RL divided by Lg times NSP square times the current in the B phase. Okay. Again, the 2 by P term would also come here. We are going to ignore that for now. So this portion is same as our previous answer. So our lambda flux linkage in the A phase due to current in the B phase comes out to negative 1 by 2 times L self times IV. Right? Everybody clear? Yep.
This value of L self is going to be the same for like all the phases, right?
L self is going to be, if the distribution is the same for all the phases. There can be cases, we might cover that in the advanced electrical exposure, one of the phase coil shorts. Then the inductance would change and the motor becomes unbalanced. We want to see how the rotor would rotate in that case. So it can change, but if the windings are all exactly the same, it will be the same. Any other questions? Can somebody tell me what that negative term means? Negative inductance, bit troubling. What does the negative term indicate? Before we jump to that, let's put those terms together. So let's take it one more step. Let's calculate what the flux in the A phase coil is going to be due to the current in the C phase winding. Because we have 3 phases in our motor. Right? So basically just complicating your midterm exam a little bit by putting one more coil. Right? And I'm going to push some current IC through this. And it's going to create some flux. Right? And the net effective flux in this air gap is now going to be phi B plus phi C. What the currents, if this current was on its own, it would have created some flux phi B. If this current was on its own, it would have created some flux phi C. When these two currents are together, it would create a net combined flux phi B plus phi C, assuming core is saturated, so superposition still holds. Right? So this is the net flux that's going to be created. So the C phase is going to have its own impact again on the A phase winding. So let me ask this question again. So I'm interested in the flux in the A phase due to current in the C phase. So what is my d lambda going to be? So it's going to be dn times phi. Can somebody fill in the subscript? It is going to be dn of which phase? A phase, B phase, or C phase? C phase. Any other answers?
A.
A phase. Rachel, why C phase?
I got confused. Never mind, I'm good.
All right. Yeah, it does get a bit confusing because what? So again, this term means the flux linking the A phase due to current in the C phase. So what we are interested in, what the flux linking the A phase coil is. So the coils that we are interested in the A phase, but the source of the flux is from the C phase current. Right. So this will be the source of the flux, which is due to the C phase current, but the coils itself is the A phase coil. So once again, we'll plug those values in. The only term that would change here is the, instead of the 2 pi by 3, you would end up with, so this is the only term that would change. Instead of 2 pi by 3, you would end up with 4 pi by 3 here. You do the integration, you get the same result again. The final answer, lambda A due to current in the C phase is going to be negative half L self due to current IC. Okay, so going back to the question, what does the negative value mean? Can somebody go back to the simple case again? How do I make this L mutual negative? What do I do to make the L mutual negative?
Put currents in the opposite directions.
Put current in the opposite directions, all right, any other way? So what can I do to the coil to make that happen? Yeah.
Reverse polarity.
Reverse the polarity. So instead of winding it like this, if I wound it the other way around, right? Because I want the currents, let's say in this case, current going into the dot, current going into the dot. So the answer both Jack gave and Hannah gave are exactly one and the same. Either you can reverse the current call this the dot and current going into this, or reverse the coil. Right? So now the current going in will create a flux in the downward direction. So if the current increases here, it would actually subtract away from the flux within this coil. So if this current is going in, it's going to create a flux like this phi A, but this current would create a flux in the opposite direction phi B. So as the current in the second coil increases, the net flux seen by the first coil will start to drop. So how will I model that? By putting a negative here. So the same thing would happen for the other coil, because this tries to create a flux in this direction, but the first coil is creating in the opposite direction. So the net flux seen by this would be whatever this created minus whatever this is trying to create. Right? So that's what we are modeling here. So if I pass some current to say I1 and create some flux linkage, and then I2 would try to counter the flux linkage because we reverse the coil direction. Right? The same you could have achieved answer that Jack gave, same can be achieved with the answer Hannah gave. Which is basically keep the coil as they are, why complicate life? And just reverse the direction of the current, either of it the same. So what is happening here is, basically whatever current we are pushing in the A phase coil is creating some flux in the air gap. B and C phase coils are going to counter that flux that we have created in the air gap if you pass the same current in other two phases as well. And we know this already from intuition, that when we pass three same currents in all the three phases, we know that the field in the air gap is going to be completely zero. Right? This is something we saw already. Let's see, the flux linkage would bear that out. If I pass IA, so the total flux linking A phase coil is going to be flux linking A phase coil due to current in the A phase, plus flux linking A phase coil due to current in the B phase, plus flux linking A phase coil due to current in the C phase. If you plug those values in, it is going to be L self right here times IA minus 1 by 2 L self times IB minus 1 by 2 L self times IC. Right? If IA is equal to IB equal to IC is equal to some IM, then it's going to be L self minus 1 by 2 L self minus 1 by 2 L self whole thing times IM, which is going to be totally zero, which correctly matches with our previous analysis that if we pass same DC current in all the three phases, the net flux in the air gap is going to be completely zero. Right? So it perfectly aligns with whatever we have analyzed so far. Is there some other way I can simplify this term? So let me bring this half, negative half L self outside. And then within bracket, I have IB plus IC. Can I simplify this any further? What do we know about a three-phase, three-wire system?
Current going in has to be the current coming out.
All right. So what would this term equal?
IA, negative IA.
Negative IA. Because we know that IA plus IB plus IC for a three-wire system is 0. So this whole term IB plus IC is just going to be equal to negative IA. So let's plug the value in. So once we plug that in, we have our total flux A total due to IA, IB and IC is going to be equal to L self IA plus 1 by 2 L self IA. Right? Because this negative cancels out this negative, you have a plus 1 by 2. So there is going to be 3 by 2 times L self times IA. Isn't it somewhat beautiful, right? You have three different currents. Of course, 3 of them are not independent. One of them is dependent on the other 2. So you have 2 independent currents. And some of the inductance, the net flux linking the coil is just purely function of one of the currents alone. The information gets folded in somehow because of the other 2 phases being in reality is dependent on one another. Because if I tell you one of the currents and its frequency and phase, you can figure out the other 2 currents because in a 3-phase system that is predetermined. So this is what our inductance is going to be, our net inductance. And we are going to introduce a new term, LM, our magnetizing inductance. So the textbook defines this as LM, I think per phase. So this is the per phase magnetizing inductance. Okay? Because what the per phase equivalent model does is it folds in the information of all the other phases into a single phase winding. because this captures the information that there is current in the B phase, there is current in the C phase, which is effectively modifying the inductance of the A phase coil somehow, right? So that's what this whole thing is. So in the textbook, I think they call LM one phase as L self, and then LM per phase as 3/2 times L self. So that's the book definition. Different books use different definition. I myself prefer keeping it as L self because it's purely the inductance of the self winding alone. And then this is per phase LM or the total magnetizing inductance because this accounts for all the effects of the other coils as well present in the winding. So this is the inductance of which phase? Is it A phase, B phase, or C phase inductance that we have calculated so far? A phase. What will be the inductance of B phase and C phase? Jonah, you want to take a guess?
Should be the same.
Should be the same, right? So it's going to be exactly the same because whatever we calculated is just for A phase, but the motor is exactly symmetric. So when we do for B and C phase, our expression, the only thing that changes is going to be so lambda B phase is going to be lambda in the B phase due to current in the A phase plus lambda in the B phase due to current in the B phase plus lambda in the B phase due to current in the C phase. Can somebody tell me what each of these expressions will come out to be? Yep, Olivia.
I have a question. So you say LM one phase equals L self and then LM per phase is 3/2 L self. What's, I think I got lost. What's the difference between the two?
So LM1 phase is just the inductance of the A phase coil due to the current in its own coil. That's it.
Oh, okay.
Right, that's the self-inductance. So assume that the B phase winding is not even there, C phase or the windings are there, but there's no current in the other two coils. You only pass current in the A phase coil, figure out what the flux linking the coil is, and you compute some inductance that is its own inductance. But now due to current, once you start passing current in the B phase and C phase, they create their own flux, which in turn links with the A phase coil, with modifying the net inductance seen by the A phase coil. Right, so that would be 3/2 times L self, which is the per phase magnetizing inductance.
I have another question, sorry.
Yep, of course.
So lambda, does lambda have a unit or is that just like a representation of the relationship?
It does have a unit. It is so your flux is Webers. Your lambda would just be Weber turns. Turns is not an SI unit, so it's like degrees or something. But yeah, it would be Weber turns. Yeah, it has a significant physical meaning to it because it's the flux. When you measure the EMF, it's actually measuring the effect of lambda. Right? It's not measuring the effect of phi directly. It's the lambda that matters. Any other questions? Yeah. All right, so can you give me the three terms? Let's start with the simple one. What would flux linking the B phase coil be due to current in the B phase coil? Yeah, yeah.
Just L self times IB.
Okay. And the first one?
Minus 1/2 times IA, and then C version, I guess, on this one.
Perfect, thank you. Again, you can take IA plus IC is negative IB, you'll get the same thing. 3/2 times L self times IB. Alright, this is the only term that changes. So this again is the LM per phase. LB. Any questions so far? Okay. So let's go ahead and derive the expression for the torque in the motor. See how much time that. If I don't have enough time to do the demo, I'll do it on Wednesday. But I'll try to get to it today. So let's see, we have again a motor. And we have some conductors at some angle alpha. Coils theta. And So far we haven't spoken about the rotor. Let's introduce the rotor. So on the rotor we have magnets. The way I'm drawing that is intentionally in a different lens. And the magnetic field of due to the rotor, let's say this is where the magnetic field is at its peak. So this is north. This is south. Again, here the drawing I've drawn is a two-pole case, but in a p-pole it will be the same thing repeated number of times. How many other poles you have? Right, just to keep the drawing simple and drawing it only for two-pole, but the derivation I'll do for a general p-pole case. So this is the axis. Let's say this is our x-axis, which is the A-phase magnetic axis. This is where the A-phase coil. If you were to draw it, we'll draw it here. And our magnet is shifted by some angle alpha at some particular time. And as time goes on, this rotor is going to rotate and this B field is going to change. So let me give the expression for what the magnetic field in the air gap due to the rotor magnet is going to look like. It is going to be some peak value times cos of theta plus alpha. Right? So for different positions in the air gap theta, the value of this is going to change. Where will it be maximum? When theta is equal to negative alpha, right? If this vector was lying along this direction, this is where the magnetic field due to the rotor magnet is going to be maximum. But we are varying the magnetic field due to the rotor magnet sinusoidally as well. How do we do that? How can we create a magnet such that the magnetic field strength of this magnet here is the strongest, and as it goes farther away, it becomes weaker and weaker. At this point, it becomes very close to zero. How do we create a magnet like that? Take a guess. So one option could be if you have some exquisite technology, you can, when you magnetize this material, you can have higher strength here, lower strength there. Right? But that is non-existent. Nobody uses it that way because it becomes quite expensive. An alternate solution would be to use segments of magnets. So you could have one magnet segment, you could have another magnet segment, other magnet segment, another segment, another segment, another segment, all stuck together, one next to another, with the central one being the strongest. As you go farther out, you have weaker and weaker magnets, right? But there's a much easier way of doing this. When we looked at the magnetic field of a magnet, and we looked at the BH curve of the magnet, what determined the field that, what determined the actual magnetic field of the magnet? Anybody? So when we looked at a BH curve of a magnet, we have B and we have H here. How do we figure out what the B field of that magnet is going to be? It is clearly not the retentivity. Right? Whatever it is retaining, that is not what the actual magnetic field of the magnet is going to be when it's operational. Yep, Lynn.
It's the ratio between like the air gap and times your magnetic field intensity.
Perfect. So you have the same answer, Kristen?
Yeah, it's like based on the constants that are deriving the core inside the reactor, right?
Yeah. What particular constant you're interested in though? It's the air gap length, right? That's the one that
Yeah.
determines.
Mu r.
Yeah, those are all going to determine the ratio, effective value of it.
Sure.
But where it lies on this, the load line is determined by the ratio of Lg divided by Lm. So we have a load line here. So if you had a magnet in an iron core, so this Lm length of the magnet and the length of the air gap. That ratio is what determines where this load line lays, and that in turn determines what the magnetic field strength of the magnet ends up being. If you increase this Lg, you go lower and lower. So as Lg increases, the load line starts to fall lower and lower, and your field strength starts to reduce. So what we do to create a B field that varies sinusoidally in a permanent magnet synchronous motor is we have the same magnet, we excite it with the same current in a core and get the same field, but then we shape it in such a way that the air gap is longer as you go farther away from the center. As you increase the air gap length, the B field starts to drop. It can have the same retentivity because you take this magnet, put it in a bunch of iron, put it in an iron core like this, put a bunch of coils, and you pass a whole bunch of current. You basically magnetize this material. That's what this BH line curve was. And once you take out the current, it would come and settle down to this retentivity value that it has. right? If there is no air gap. But then you can have it such that the length of the air gap is very large here or very small here, so that we have higher magnetic field strength here and sinusoidally reducing magnetic field strength there, right? And the way you compute what this shape should be is a pretty complicated problem because it's not a linear curve, pH curve. It's a non-linear curve. So you would have to use some kind of numerical solver to figure out exactly what the air gap length should be at each point to get this characteristic. So you would shape the material of the magnet like this. When you form the material itself, once you create the magnet, you don't want to chip away element of magnets to create that larger air gap. Because magnets are quite brittle, they'll break out. So when you create the material itself, you'll create it in such a way with the shape with larger air gap length, and it's called shaping the magnet, and you can create any kind of B field in the air gap that you want just by shaping it. Right? So once we have the B field in the air gap, okay, so now this magnetic field that we have, that is going to interact with the conductors in the stator, which is carrying current, to create a force on the conductor. Right? And we have an expression for that. So the differential force created on the tiny set of conductors that we have there is going to be L times I cross B, where I is the current going into the whole set of conductors. So I itself is going to be equal to L times dN times the current in the A phase times the magnetic field due to the rotor, right? So that is going to be VR some P cos of theta plus alpha. This dN is the conductor density for this tiny set of conductors that I've chosen. Again, the B field is varying sinusoidally. So I have to set it up as an integral problem again. So the B field due to the rotor is varying sinusoidally, and the conductor density is also varying sinusoidally. There is no way I can just look at the B field at one point, look at the conductor density at one point, multiply it and call it a day and say that everywhere else will be the same. It is going to completely vary. So what I'm going to do is take this tiny section of conductors, spread over some angle d theta, and then I'm going to figure out what the force experienced by that set of conductors is. To figure out the total force, I'm just going to integrate this from 0 to 2 pi all the way. Right? So the conductor's density there for the tiny portion that I've chosen is going to be ns divided by 2 sine of p by 2 times. Oh, I said I'll do it for a generic p by 2 pole case. So p by 2 times theta. So this term changed it from theta to p by 2. Even though on the board I have drawn just a 2-pole motor because I will be terribly bad at drawing a 4-pole case, but we are going to do it for a general 3-pole case. So the distribution, again, the answer I think Hannah gave, m by 2 remains the same, sine of p by 2 theta, this is the only thing that changes, times d theta, the number of conductors, the distribution over the tiny distance, L times R times p by 2 times theta times d theta times BR times IA times BR peak cos of p by 2 theta plus alpha. How will I get the torque experienced by the incremental set of conductors? That is just the force. How do I get the torque? Simple question.
What about radius?
Multiply by radius. So again, I'm multiplying it by the rotor radius. In reality, it should be the radius of the rotor plus the air gap length plus a little bit distance inside where the conductors are located on the stator. But the air gap length is quite small. So the rotor radius in the homework that I gave you, I think is like 50 centimeters or something. Or it might be slightly lower, 10 centimeters or something. While the air gap length is, I think, 1 millimeter. So it's orders of magnitude lower that you can just assume to be just R across the system times this whole expression that I had here. So d tau is going to be R times L times ns by 2 times sine of theta times v by 2, blah, 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 so on and so forth. How do I get the total torque experienced? What will be my range of integration to get the total torque experienced by all the conductors there? It's going to be 0 to pi, 0 to 2 pi.
0 to pi.
Who said 0 to pi? Why pi?
Like you'd count it twice.
Did I count that twice though? I took the radius and multiplied So what we have written there, good answer. So I took the radius and I multiplied by the force experienced by conductors here. If I had taken the diameter, I would have considered this part as well. Okay, but I only took from this part to this set of conductors what the force is being experienced by it. I haven't accounted for the other side. So you have to be quite careful when you do the integration to set the limits correct. Is it clear, Jack?
Yeah.
Right. So the total torque is going to be from 0 to 2 pi d tau. So plug in all of these values. You have this sine of p by 2 times theta, and then cos of p by 2 times theta plus alpha, and you plug in those values and integrate them. The result that would come out of the integration r times l times dr times ns divided by 2. Let me put this dr on the other side. Ns divided by 2 times dr times I times sine of alpha. Right? So let me just quickly double check whether that expression is right. Oh yeah. Okay. Oh, I missed the item. So when we do this portion of the integral, so let me just write this down. You can double check. Later sine of p by 2 times theta times cos of p by 2 times theta plus alpha d theta, that comes out to 5 times sine of alpha. Right? That's what comes here. Rest are all the constant terms that I've collected. So this is the torque experienced by the stator due to the magnet, due to the current in the A phase winding. Right? But we have latched down the stator. The stator is not going to rotate. So we know that if the stator is experiencing the force, the rotor experience equal and opposite force from Newton's law. So whatever the force the stator is experiencing, since the stator is latched out, the rotor's work is going to experience the force and it's going to start to rotate. Right? The torque experience is going to be exactly the same value. And we can prove that quite easily when you go to the lab. Hold on to the rotor and excite it, the stator will start spinning. There's nothing special about the stator, it's just that it's usually latched down so it doesn't rotate. And when Jonah, you did the experiment, you basically rotated the stator and broke the brush. So there is nothing special about the stator, it can rotate as well. Alright. So let's go back to this expression. Torque in the A phase is pi RL ns by 2. Couple of interesting observations here. Dr Ia sine of alpha. So if you look at the torque, it does not depend on the number of poles at all anyway. Alright, you can double your poles, the torque in the motor doesn't change as long as the conductor length, the conductor number doesn't change. Alright, this is the answer that Lily gave a couple of weeks back when I asked what is the advantage of going to higher pole count, and the answer was you can increase the torque. But the condition is that also means that the number of conductors should have increased for the torque to increase. If you have the same number of conductors, the torque will not increase even if you increase the pole count. But increasing the pole count means that the flux density concentration over any particular pole phase would reduce by half if you double the poles. That will allow you to either double the number of conductors or shrink the yoke length so that you can either save the energy density by shrinking the torque and power density of the motor. You can increase it by reducing the core size as well as the yoke size, or you can double the conductor and then increase the torque that you can generate for the same set of motor structure. Alright, so that's why you would go to higher pole count. So the confusion usually comes because people like to rewrite this for whatever purpose I don't know as P by 2 RL times NSP. Right, take this 2 here and then BR IA sine of alpha. NSP itself is NS divided by P. So this PP gets cancelled, it just becomes NS by 2. So typically textbooks would give you this formula, and that is the cause of concern because people always think, oh, if I double the poles, I'll get higher torque. That confusion comes from this expression that we have. That is not the case at all because the NSP hides away the NS divided by P there term present there. Okay, so the second thing, let's say I pass some current in this. Will this start to rotate? Let's say I pass sinusoidal currents into the motor. Will it start to rotate? Not at all, right? Because if I convert this into some Im sin omega t or let's, since we are doing cos, let's keep it as cos. There is going to be a torque produced, but the torque is going to vary with time. Right? So the average net torque seen by the rotor is going to be 0. So it is not going to rotate the system. And we already know this. In the one-phase motor, we saw that the B field effectively splits into two parts, going one direction and the other direction, and that is going to pull the rotor in the equal force. So a rotor that's static on with equal force on both sides, and it's not going to rotate the rotor. Mathematically, we have just proved the same thing, that we have a torque that goes positive and negative over time, and over a single cycle, the net torque produced seen by the rotor is going to be absolutely 0. Right? Now let's introduce B phase as well. So torque produced due to current in the B phase. Whatever torque we calculated there is purely due to current in the A phase. The only thing that is going to be changing right now, the BR cos P by 2 times alpha, that is going to remain the same. Right? Because BR is going to be wherever it is going to be, the rotor magnetic field. But the conductor density distribution, that NS by 2 times sine of P by 2 times theta, that term will change for B case. So this term is not controlled by the stator. This is an independent entity, that remains the same. This term would have another factor minus 2 by 3 times pi when we go to B phase, right? Theta due to B phase. And then you can do the same problem all over again, set up the math, do the integration, and you will end up with your expression for torque due to B phase as pi times R times L divided, no LG, NS divided by 2 times BR times IB times sine of alpha minus 2 pi by 3. And then the same for when you have C phase current, you'll end up with pi RL NS divided by 2 BR IC sine of alpha minus 4 pi by 3. What will happen when what will happen to the net torque when I have all three currents phase shifted by 120 degree? So this current itself is going to be Im cos omega t minus 2 pi by 3. This current is going to be Im cos omega t minus 4 pi by 3. And if I sum up all of these three, what will it look like? You have seen this expression already. When you have cos omega t minus 2 pi by 3 times sine, instead of sine, you can think of this cos 2, doesn't really matter. But sine of alpha minus 2 pi by 3, and then you have sine of alpha minus 4 pi by 3, and then there's sine alpha cos omega t. Right. What have we set up? It's basically the same expression you would have gotten when you solve for the space vector, right? Rotating to the air gap. You had these combinations of one time varying component and another component which was basically shifting it by e power j0, e power j2 pi by 3, e power j4 pi by 3. So the final expression that you would get out of this would be 3 by 2 times pi RL NS divided by 2 times BR times the current magnitude Im times sine of alpha. Right? So this will be the total torque created by the motor. Sorry, this one motor is plus omega t. So once you plug in these values, again the derivation is posted online. This is the final expression that you'll get. Will the motor experience a torque? No. Will the rotor be experiencing a torque? So the expression is this one. Will the motor be experiencing a torque? Let's say the rotor is standing still. And this is varying sinusoidally, right? Because omega t is varying sinusoidally. What will be the net torque? Same problem as what we have on the right there. My torque is going to vary sinusoidally if my rotor is at standstill. So the net torque created by this motor will be 0. Okay, so this is the biggest problem with the permanent magnet synchronous motor, that if the rotor is not rotating and you apply frequencies at 60 Hertz, then the motor will not start to rotate at all because the net average torque is still 0. And this was the first problem we saw why in the permanent magnet synchronous motor weren't common back in the day when power electronics wasn't there, but it's becoming more common now. Because the rotor comes to a stop because you apply a lot of large load, then the rotor will not start to rotate again because the average torque seen by the rotor would be 0. When will the average torque not be 0? What will be the constraint on alpha for the average torque not be 0? So the way we derive these expression, you add it. So if I flip this current, let me make it simple for you. If I flip this to plus 2 pi by 3 and make this plus 4 pi by 3, that would basically reverse the angle of rotation. What will be the constraint for alpha so that the torque is non-zero? Yep, James.
Not equal to omega t or less.
Should it not be equal to omega t? Is that the only condition? Olivia,
I was thinking, so.
right? Any other answers?
It's not equal to 0.
Not equal to 0. It's just not equal to 0 the constraint.
Alpha and omega need to be equal.
Olivia?
Don't they need to be equal?
They need to be equal and phase shifted. Is that what you said, Hannah?
No, but that's
Oh,
okay.
what did you say? What is the phase shifted? What do you
You
say?
said opposite, but that doesn't make sense.
Opposite. So let's look at all the cases. If you put 0 here, you end up with the same problem as before. You have sine of negative omega t. Your torque is varying sinusoidally. Net torque is 0. If you put omega t, the net torque is again 0. Right? So, but if you put omega t plus some phase shift phi. So this omega t gets cancelled. You have some sine phi. Alright, so then in that case, you will produce a net torque in the system. So if the rotor rotates at the same speed as your stator magnetic field, the air gap, the magnetic field that we created is rotating, then you can produce a net torque in the system. But if it slows down, right, and you cannot recover the speed back up again at steady state, then the system will come to a stop and then you'll end up burning the winding because there is no back EMF that's created. So let me just take 2 more minutes and with that I'll finish it off. So let's diagrammatically look at what's going on. We shouldn't have deleted. Okay. So let's say our magnetic field in the air gap due to the stator currents is in this direction, space vector. Right? So at some time t equal to 0, the B space vector is like this. As time goes on, this whole picture is rotating in time. This is not a phasor, this is a space vector. I cannot draw a rotating field, so I'm just going to draw one line at one particular time. But you have to physically visualize this as rotating continuously. Right? If my B field due to the rotor is rotating at the same speed as this magnetic field, then I can create torque given that this B field lags this B field by some angle phi, right? If that phi angle is 0, if this B field is aligned with this B field, there is no torque produced. If it is lagging this B field, it's going to produce more and more torque. And the maximum torque will be produced when it's lagging by a factor of pi by 2. So if you look at the motor, so this is going to be our electromagnetic torque, total electromagnetic torque, tau m. And that is going to vary as a function of delta. And as this angle goes to 90 degree, that is when you will produce the maximum torque in your motor. Right? So let's look at what's going to happen. Let's say we are starting, initially we are at this point, some angle delta 1, and the torque is some Pem1. And as soon as I apply an additional load torque, what is going to happen? Can you tell me what the sequence of events is going to be? So let's say the motor is operating at steady state, it's rotating at some speed. Again, this and this have to be rotating at the same speed for any torque to be produced, but it's lagging by some angle delta 1. So let's say this phi is some delta 1 load angle, right? And this is the torque that's being produced. Let's say I increase the load torque now. What is the first thing that's going to happen? What is going to happen to the speed when I increase the load torque? So the speed is going to initially be a constant given by our synchronous speed, which is going to be equal to 120 f by p that we just calculated. Right? When I increase the load torque, what is going to happen to the speed? Why would it go down?
It's essentially like adding more resistance into a circuit.
Alright, but mechanically, can you explain me what's going on? So when the load goes up and the speed is the same, the power going into the load has increased. Where is that additional power coming from? Where is that energy coming from? Is it coming from the electrical system right away? No, because the electrical system has impedance, so it takes a while for the current to build up before it can satisfy it. Where is that energy coming from?
The inertia of the motor.
The inertia, perfect. So it's coming from the stored energy in the rotor, half j omega squared. So if you take energy out of it, omega has to go down. So speed has to come down. When the speed comes down, what happens to the angle between the stator magnetic field and the rotor magnetic field?
Decrease.
Does it decrease? So basically think of it as you and your friend are running in parallel, but your speed has come down. What happens to the separation between you and your friend? Your separation would start to increase, right? So this is lagging a little bit while this is going faster. So this comes back a little bit. So the phi has now increased. So you went from a load angle of delta 1, now you go to a new load angle delta 2. Right? What happens when we go to a higher load angle? What happens to the torque?
Increases.
Increases because of this characteristic curve that we have. So our electromagnetic torque increases. You see the nice feedback loop that is has shown. You increase the load torque, the motor can reach steady state only if the load torque reaches the same as the electromagnetic torque. When you increase the load torque, the speed came down, the load angle, the separation between the stator and the rotor magnetic field increased because the load angle increased. The increased load angle then creates more electromagnetic torque, which can now match the added load torque, and then the motor can now rotate at the stable speed now. Alright? What will be the speed once it reaches steady state? Will it go to a reduced speed and stay there? What is the name of this motor? Synchronous motor. So the speed would have to come back up. So it would execute a nice oscillation, it will come down. So it will basically go to a little bit higher load angle, come back, and settle down to this new load angle. But the speed would always have to be synchronous speed. If the speed is not synchronous, the torque would go to zero. The only condition that will satisfy is when alpha equal to omega t plus a steady phase shift. This phase shift cannot vary as a function of time. If omega 1 is not same as this omega is not same as this omega, then there will be always a net average torque being zero and you won't reach steady state at all. Okay, so just 10 more seconds. What will happen if I reach the peak value and I increase my load demand just a little bit more? Go down. So if I go to the peak torque value and I still ask for more torque, then we know from our logic that the energy has to come from inertia. So the angle would go even backwards. So 90 is the maximum. After that, it will go even backwards because you're drawing energy from the inertia. Motor is slowing down. Separation between you and your friend is increasing. Right? So the delta angle is keep on increasing. But the problem is on the other side, the feedback loop is negative. When the delta angle is increased, then you're producing lesser torque than what the load needs. That means you're going to take out more energy from the inertia. That means you'll lag even further. You'll go further down. You'll go further down until you come to a full stop. Right? So that's what happens in a permanent magnetic synchronous motor. Once you reach the peak torque, you still demand more torque. The rotor will come to a stop. And that is a disaster because we haven't dealt with back EMF yet. We'll do it next week. But the back EMF is not present when the rotor is not rotating. So you'll have huge amount of inrush current and the motor will burn out or your magnets will get demagnetized. With that we are done, we'll continue next week. The last question, the homework for this week, we still need to cover the equivalent circuit. I'll extend the timeline for the homework 10 by a couple of days. Once we cover it on Wednesday, we'll be able to answer it.